Welcome to the first lecture of this course titled Motion in a Straight Line, and we will begin with what is called average motion. To see what is meant by average motion, suppose that you are at your home here, and you drove your car to the pizza place for 15 minutes, and let's say that the pizza place is 10 kilometers far from your home. After you arrived at the pizza place, you grabbed your pizza and went back to your home again in another 15 minutes. Now, we can say that your average speed is the total distance you traveled, total distance divided by the total time. And in this case, the total distance is 10 kilometers going to the pizza home and 10 kilometers coming back, going to the pizza place, and 10 kilometers going back to your home, which is 20 kilometers divided by half an hour. 15 minutes plus 15 minutes is half an hour, and this is equal to 40 kilometers per hour. This is your average speed. Now, to describe your motion more precisely, we introduce x, and x in this case gives your position. And if we choose our coordinate system to be x, which is the position in kilometers, and t, which is the time in minutes, and you are at your home here at the origin, which is 0 position and 0 time, and after 15 minutes you were here 10 kilometers from your home, your origin, and in the other 15 minutes, i.e. after 30 minutes, you went back again to your home, which is the 0 position. Now, in the case we are going to calculate the average velocity, and the average velocity in this case is the displacement over the total time. The displacement over the total time. What is the displacement? D is x2 minus x1, or we can call it delta x. So V bar, i.e. V average, is equal to delta x over delta t. And in this case, delta x is 0, which is 30 minus 0 minus 0 divided by total time. In this case is 30 minutes or half an hour, and this is equals to 0. So the difference between average speed and average velocity average velocity is that the average speed is the total distance traveled over the total time, while the average velocity is the total displacement, which is the difference between the initial and final positions divided by the total time. Exercise 1 on average motion. Starting from home, you bicycle 24 kilometers north in 2.5 hours and then turn around and pedal straight home in 1.5 hours. What are your displacement in the first at the end of the first 2.5 hours, average velocity over the first 2.5 hours, and average velocity for the homeward leg of the trip, and displacement for the entire trip, and average velocity for the circuit? This is a comprehensive question, a comprehensive exercise about average motion. You are here, for example, you go north 24 kilometers, and then in of course 2.5 hours, then you pedal around, you turn around and pedal straight home in 1.5 hours. So this is your home at 0, 0. Now this is a one-dimensional kinematics problem that involves calculating your displacement and average velocity as a function of time. Now we have two parts here. The first part is traveling north, and the second part is traveling south. So if we plot here the displacement as a function of time, we can simply use the definition of the average velocity and average speed to find them from the plot. So we plot here the displacement versus time. So here we have distance in kilometers, and here we have time in hours. At the beginning you are here at 0 distance, 0 time. After 2.5 hours, you are here at 24 kilometers apart from your home, and then after 1.5 hours, or i.e. after 4 hours from the beginning, you are again at your home. This is the distance time displacement graph. So this point is 2.5 and 24, so 2.5 hours, 24 kilometers, and this point is 4 hours, 0 kilometers. In order to find the displacement at the end of the first 2.5 hours, we simply write A delta x, because we need the displacement, which is x2 minus x1, and x2, as it is clear here, is 24, and x1 is 0, which is 24 kilometer. This is the displacement at the end of the first 2.5 hour. The average velocity B, the average velocity over the first 2.5 hours, is simply V average is delta x over delta t. This is 24 over the time for the first part of the trip is 2.5, and 24 over 2.5 is simply 9.6 kilometers per hour. C, we need to find the average velocity for the homeward leg of the trip, i.e. this part of the trip, and the velocity average is x t2 minus x1 over t2 minus t1, which is x2 here is 0 and x1 is 24, t2 is 4 minus t1 is 2.5, so this is minus 24 minus 24 over minus over 1.5, and this is equal to minus 16 kilometers per hour. Now we can see that the velocity for the homeward leg of the trip is negative. That because we choose the north direction to be positive, and the direction of motion for the homeward leg of the trip is negative, so the velocity is negative. D, we need to find the average velocity of the trip, and the average velocity of the overall trip is x2 minus x1 over t2 minus t1. This is equal to 0 minus 0. This is final point, this is the initial point, over 4 minus 0, and this is equal to 0. This is the overall average velocity of the trip. Exercise 2 on the average motion. Taking the Earth orbital speed to be a circle of radius 1.4 times 10 to the 8 kilometers, determine the Earth's orbital speed in meters per second and miles per second. So we have the Earth is orbiting around the Sun, as we know, and the radius of this orbital motion is 1.5 times 10 to the 8 kilometers. We need to determine the Earth's orbital speed in meters per second and miles per second. In order to do that, we can simply use the equation v equals distance over time, and the distance here is simply the circumference of the orbit of the Earth, and the circumference is 2 pi r over the time, which is 365.25 days. And if we convert it to seconds, so let's write first of all 2 pi r, which is as mentioned here 1.5 times 10 to the 8, 1.5 times 10 to the 8 kilometers, so it is 1.5 times 10 to the 11, 1.5 times 10 to the 11 meters over 1 year times 365.25 days times 24 hour per day times 60 minutes per hour times 60 seconds per minute. And if we calculate this, we get 3 times 10 to the 4, 3 times 10 to the 4 meters per second. And to find this value in miles per second as wanted by the problem, by the exercise, miles per second, we just convert meters to miles, and the conversion factor of meters of miles to meters is 1 mile equals 1609 meters. So V is simply equal to 3 times 10 to the 4 meters times 1 mile over 1609 meters. So this is 1 mile per meter per second. Calculating this gives 19 miles per second. Directions. And coordinate system. Coordinate system. Now, as we discussed in the last lecture, we defined the displacement as x2 minus x1. Now, it is matter whether you go right or left, up or down, east, west, north, south. So the displacement therefore includes not only how far, but also in what direction. So for motion in a straight line, we can describe both properties by taking position coordinates to be positive in going in one direction and negative in going in the other direction. For example, we can consider that going to the right is a positive direction and going to the left is negative direction. For example, when we say displacement delta x equals 2 meters, that means 2 meters to the right. Delta x is going minus 4 meters. We mean here that 4 meters to the left, or if we are talking about motion straight line in the y-axis, delta x equals 2 meters may mean 2 meters up, and minus 4 meters may mean also 2 meters down. So in order to take into consideration the direction, we use the minus and the plus sign for the displacement quantity. In order to clarify this, let's take this example. In this example, suppose that you are going to travel from Houston to Kansas and you need a cheap flight. From Houston to Kansas, let's this be Houston, and this is, for example, Kansas City. And in order, which is 1,000 kilometers far, 1,000 kilometers. In order to have a cheap flight, you have first to travel to, or you have to have a connect in Minneapolis, which is 700 kilometers north to Kansas City. So you have first to connect at Minneapolis, which is 700 kilometers away from Kansas City. So your trip will be Houston, Minneapolis, and Kansas City. And the flight to Minneapolis takes 2.2 hours. So from Houston to Minneapolis, here we have 2.2 hours. Then you have a 3-minute layover at Kansas. We have here 3 minutes layover, and then a 1.3 hours flight to Kansas City. So when you went back to Kansas, you will have 1.3 hours. So the total time is T total equals 2.2 plus 1 or plus 0.5 plus 1.3, and this is equal to 2.2 plus 0.5 is 2.7 plus 1.3 4 hours. This is the total time. If we need to find the average velocity, V average equals to delta x over delta t. And if we choose Houston, for example, to be x equals 0, then the total displacement, or the displacement, is equal to 1000 minus 0. 1000 is the position at the end point, which is Kansas City, minus 0 is the position of the starting point, divided by the total time, which is 4 hours, and this is equal to 250 kilometers per hour. And if we want to find average speed equals total distance divided by total time, and this is equal to, the total distance is the distance from Houston to Minneapolis, which is 1,700 kilometers. 1,700 plus the distance from Minneapolis to Kansas, which is 700 kilometers. So plus 700 this, and divided by the total time, which is 4 kilometers. So 2,400 over 4 equals 600 kilometers per hour. Instantaneous velocity. Now we learned before that if we need to find the average velocity from the xt graph, let's have this graph, and we need to find the average velocity of the object from t1 to t2, we simply say v equals x2 minus x1 over t2 minus t1. That means that we are calculating the slope of the sector between these 2 points. The point represents t1 and the point represents t2. Let's this be x1 and this x2. Now, as the line joining the 2 points is get smaller, let the line be here, for example, the 2 points are coming closer to each other. The 2 points that we are calculating the average velocity between them is becoming closer. Now, at a point, the 2 points will be 1 point, and this point, in this case, when the 2 points becomes 1 point, then we are calculating the slope of the tangent line of a point, and the slope of the tangent line of a point is called the slope of the tangent line is called physically the instantaneous velocity, and we describe this as the limit of delta x over delta t as delta t approaches 0, or mathematically calculus tell us that we can write limit of delta x over delta t as delta t approaches 0 as dx by dt, the first derivative of the position with respect to time. And we can find the derivative for any function. For example, function f of x equals ax to the n, for example, then df by dx or f prime is simply a n x to the n minus 1, and this is called the first derivative of the function of x as with respect to time. And in this case we calculate the instantaneous velocity of the object. So in the case we have a graph of the distance as a function of time, for example this graph, and we need to find the velocity at any point. Let's be this point, for example. We just simply find the slope of the tangent line of the graph at this point, and we can distinguish whether this slope is, or whether this velocity is positive or negative from the sign of the slope. For example, slope 1, this is slope, is positive, so the velocity from here, from point A to point B, is positive, and at B exactly we can see that the tangent line is horizontal, so the slope of this tangent line is 0 and the velocity is 0. In this case the instantaneous velocity is 0, and after point B we can see that the tangent line is negative because its slope is negative, so the velocity changes sign from positive to negative, from positive here to negative here. Let's take another graph. For example, if we have this graph for x and t, this graph, we can see that at any point of this graph, if we find the tangent, if we find the slope of the tangent at any point, we can conclude that the slope of this tangent is equal to the slope of the line itself. So the velocity, because the slope is constant at any point here, then the velocity at any point on this graph is constant. So we can conclude that instantaneous velocity is equal to the average velocity. Instantaneous velocity is equal to the average velocity if the relation between the distance and the time is linear. If the relation between x and t is linear, then v instantaneous equals to v average at any point. Let's take an example. If the altitude of a rocket in the first half minute of its ascent is given by x equals bt squared. The altitude of the rocket in the first half minute of its ascent is given by x equals bt squared, where the constant b is 2.90 meters per square second, and the question is find the general expression for the rocket's velocity as a function of time. Find the general expression for the rocket's velocity. Now, the general expression for the rocket's velocity v is equals, as we know, v is equal to dx by dt. So we need to derive this relation, x equals bt squared. As we learned before, the derivative of this function is 2bt. 2bt. This is simply the expression for the instantaneous velocity of the rocket at any time. And number 2, this is A. B, find the velocity at t equals 20 seconds. Find v at t equals 20 seconds. Simply v equals 2b times 20. This is equal to 2b, which is 2.9 times 20. This is 116 meters per second. C, find an expression for the average velocity. So we need to find the average velocity. Average velocity, as we learned before, is equal to delta x over delta t, and or the displacement over the time. The displacement over the time. And the displacement, as we know, delta x, as it is given by the problem, is bt squared. So we can simply write bt squared over delta t is t, which is the time. We simply cancel t with the square to get bt. So to find the average velocity, we simply multiply the constant b by the time. We can notice here that the instantaneous velocity v, this velocity, is equal to 2 is equal to 2 v average, because v average is bt and v instantaneous is 2bt. So the instantaneous velocity is twice the average velocity. Acceleration. Now the acceleration A is defined as the rate of change of velocity, And as in velocity, we have average acceleration and we have instantaneous acceleration, where average acceleration is the ratio of delta V over delta T. So A average is equal to delta V, the change in velocity over the change in time, and instantaneous acceleration is equal to limit of delta V over delta T as delta T approaches 0. Or we can simply say acceleration, instantaneous acceleration is dV by dt. dV by dt. The acceleration in one-dimensional problems is either in the direction of the velocity or opposite to it. So we can check that by calculating the acceleration to determine whether it is in the direction of velocity or the opposite to it. And notice here that to find the acceleration from the velocity time graph, if we need to find the acceleration at any point B, then simply we have to find the slope of the tangent line of the graph at this point, at the point needed. This is the tangent line of the point of the graph at point B, and the slope of this tangent line, simply if we calculate the slope, delta V over delta T, will give me the acceleration or the instantaneous acceleration of the object at point B. So what is the relationship between position, velocity, and acceleration? What is the relationship between them? Now, we said that V is the ratio of x with respect to t, and A is the ratio of V with respect to t. And can we extract the graph of the velocity and the acceleration from the graph of position? Let's say that. Suppose that we have the graph or the relationship between the height of an object as a function of t, and this object, the height of the object is given by this graph. So this object starts from zero position, zero height, and then its height is increasing and reaches maximum at some point here, some point B. It reaches maximum, then the height is decreasing back to zero. Can we find, or can we graph can we sketch the graph of velocity from the graph of position? This is the position graph. Now, if we given that the initial velocity of the object is v0, then we know here from this graph, from the graph of position, the first part of the graph tells us that the velocity of the object is positive, but it is decreasing with time. Why it is positive and why it is decreasing with time? It is positive because at any point in the first part of the graph, at any point if we draw the tangent, we can conclude or we can see that the slope of this tangent is positive. Why it is positive? Because the difference in y2 minus y1 is always positive, because y2 at any time is greater than y1, and this extends from 0 to point B. So in the first part the velocity is positive. Why it is decreasing? Because the slope is decreasing. Why the slope is decreasing? Because the difference in y is getting smaller as we go up. The difference in y here at a given t is greater than here, so it is decreasing. So we can imagine that if the initial velocity of the object is v0, this is v and this is t, we can conclude that the shape of the graph of v versus t is so. And after point B, this is point B, after point B, we can conclude that the velocity is negative. Why? Because the slope at any point is negative because y2 is less than y1. So y2 minus y1 is negative and the slope is negative and the velocity is negative. So we have to continue drawing this line. This is the graph of v versus t for an object moving upward. So we extracted here the graph of the velocity from the graph of position. This is the graph of velocity. Now, in the second step, we are going to extract the graph of the acceleration from the graph of velocity. This is A, acceleration, and this is T. The shape of the velocity graph is straight, and we know that the straight line has a constant slope. And because it has a constant slope, it has a constant acceleration. So the graph of the acceleration is constant, but we can see from velocity graph that the slope of the graph is negative because time is getting smaller. So the graph is negative. So we can conclude that the graph of the acceleration is constant and negative. This is the graph of the acceleration. To find its value A, we can simply find the slope of the slope of the velocity, the slope of the velocity graph. This is this graph at any 2 points because the slope is constant at any 2 points, and find by this way the value of the constant acceleration of this object. Now let's summarize what we have learned here about the relations. Till now we know that v equals to dx by dt and A equals to dv by dt, which is d2x, the second derivative of the position with respect to time. These are the important two relations that we learned so far. Constant acceleration. Constant acceleration. Now in this chapter we are going to derive the equations of motion in the case of constant accelerations. Now the description of motion has an especially simple form when the acceleration is constant. Suppose an object starts at time t equals 0 with some initial velocity, let's say v0, and constant acceleration, let's say a. At some time t, it has a velocity of v. So this be t1 and this be t2. At t2, the velocity is v. So the initial velocity is v0 and the final velocity is v. Because the acceleration constant, its average and instantaneous velocity are identical. So A average equals A instantaneous equals V minus V0 over T minus T0. And we always suppose that T0 is 0, so A average equals A instantaneous. So this is A instantaneous. A average equals A instantaneous equals V minus V0 over T. Or if we rearrange the terms, we get V equals V0 plus AT. This is the first equation of motion in the case of constant acceleration. Now, and if we determine velocity as a function of time, we can consider position with constant acceleration. Velocity increases steadily, and thus the average velocity over interval is the average of the velocities at the beginning and at the end of the interval. So the average, as we know before, delta x over delta t. Because velocity increasing steadily, that's because acceleration is constant, of course. We can consider that the average velocity over an interval of time is the average of the velocities at the beginning and at the end of that interval. So V average, we can consider it to be 1/2 V0 plus V, or V0 plus V over 2. This is the same. Now, and we also know that V average is equal to delta x over delta t, and this is equal to x minus x0 over t minus 0. Now, if we write this equation as a function of t, we can write x equals x0 plus v average t, or x equals x0 plus, instead of v0 we are going to substitute this equation. So x equals x0 plus 1/2 v plus v0 times t. And this is the second equation of motion with constant acceleration. Let's call this equation 1 and this equation 2. Now let's rewrite equation 2 in another form. X equals x0 plus 1/2. Instead of v, we can write v0 plus at and plus v0 times t. So what we get here is x equals x0 plus v0 t plus 1/2 a t squared. This is the third equation of the equations of motions with constant, the equations of motion with constant acceleration. Now we can also write x minus x0 from equation 2 again. X minus x0, we can write it as 1/2 v plus 1/2 v plus v0 t, 1/2 v plus v0 t. And if we write instead of t, if we write v minus v0 over a, v minus v0 over a, and this comes from the first equation, from this equation, t equals v minus 0 v0 over the acceleration, then x minus x0 becomes x minus x0 equals 1/2 v plus v0, this is v plus v0, times t, which is v minus v0, divided by a. Then we can rewrite this equation if we substitute instead of v minus v0, v plus v0 times v minus v0, v squared minus v0 squared, then x minus x0 equals 1/2 v squared minus v0 squared over a, or 2a x minus x0 equals v minus v0 squared, or v squared equals v0 squared plus 2a x minus x0. And this is the fourth equation of the equations of motion and constant acceleration. Now let's summarize the equations of motion. So we have 4 equations of motion for constant acceleration. The first equation is v equals v0 plus at. In this, we use this equation when x is not known, so it does not contain x. So what does this equation contain is v and v0 and t. The second equation is x equals x0 plus 1/2 v0 plus v times t, and x, third equation, x equals x0 plus v0 t plus 1/2 a t squared, and the fourth equation is v squared equals v0 squared plus 2a x minus x0. Now let's see this example. A jetliner touches down at 270 kilometers per hour. The plane then decelerates, i.e. undergoes acceleration directed opposite its velocity at 4.5 meters per square seconds. So we have an initial velocity v0 and the final and the acceleration, which is minus 4.5 meters per square seconds, and the final velocity is 0. So what is the minimum runway length on which this aircraft can land? Here we have a problem involving one-dimensional motion with constant acceleration, and the object of interest here is the airplane. So the airplane here has v0 and here has v equals 0, and along the runway the acceleration is minus 4.5 meters per square second. We first change the units of velocity of the initial velocity of the jetliner, which is 200, and so V0 equals 270 kilometers per hour. To change it into SI units, we multiply by 1000 meters per kilometer times 1 over 3,600 hours per seconds to get V0 equals 75 meters, 75 meters per seconds. So we have V0 and V and A, and we need to find the length of the runway, so we need to find X. And to find X, simply we use the first equation of the equations of motion, which is V equals V0 V squared, or the third equations of the equations of motion. V squared equals V0 squared plus 2A x minus x0. V squared is 0. V0 squared is 75 squared plus 2 times minus 4.5, which is the acceleration, times x. Because here we suppose that x0 is the origin, is at the origin, or the point at which the jetliner touches the ground, to be 0, so x0 is 0, and we can find x from this equation. X equals to minus 75 squared divided by 2 times minus 4.5, and this is equal to 625 meters. This is the length of the runway. Example: a speeding motorist zooms through 50 kilometers per hour zone at 75 kilometers per hour. That's 21 meters per second. This is the velocity of the speeding motorist without noticing a stationary police car. There was a police car there. The police officer immediately heads after the speeder, accelerating at 2.5 meters per square seconds. When the officer catches up the speeder, how far down the road are they? Asking about X, and how fast is the police car going, and V. This is a one-dimensional problem involving a constant acceleration, of course, but here we have two objects. The speeder, we have the speeder, and we have the police car. We have two objects. Each object has its own velocities, initial and final, and acceleration. For the speeder, for example, we have a constant velocity. The velocity of the speeder, Vs, is equal to 75. No, it is. The velocity is 75. Yes, 75 kilometers per hour, which is 21 meters per hour. This value. And for the police car, we have V police initial, V police 0 is 0, and A police is equal to 2.5 meters per square second, while the acceleration of the speeder is 0. At some point, the two cars coincide. The two cars, from the point the police car starts to the point they coincide, they both have the same x. So we have x for the speeder and x for the police car are the same. So we can find x for the speeder is v0 t, which v0 v0s, so vs0 v speeder 0 t is the distance traveled by the speeder at the same time at the time t. Because the acceleration is 0, the distance traveled by the speeder is v0 t, and x for the police car is v police 0 t plus 1/2 a police t squared. And because the two distances are the same, we make xs to equal xb. So v0 vs 0 t equals vb 0 t, which is 0 because the police car starts motion from 0. So we simply write 1/2 a police t squared. Now solving this problem gives t equals 0. This is the trivial case, which is the case when the police car passes beside the speeder. We are going to find the second value of t, which is from this equation v0 vs0 divided by 1/2 ab, which is vs0 is 21 yes, divided by 1/2 times the acceleration of the police car, which is 2.5. This is equal to 16.8 seconds. Now after finding time, we can simply find x, because x, whether we find it for the speeder or the police car, is the same. So we find x from the relation vs0 t, which is 21 times 16.8, and 21 times 16.8 is equal to 352.8 meters. 352.8 meters. This was the distance between the police car and the speeder at the time the policeman decided to follow the speeder. Now, to find the velocity of the policeman at this point when he catches the speeder, we can simply apply this equation: v police equals v police 0 t, no, v police 0 plus, because we have time, we can simply use the first equation, plus a police times t.
which is B police 0 is 0 plus A police, which is 2.5 times T, which is 16.8. So 2.5 times 16.8 is simply, and this is equal to 42 meters per second, and this is equal to 151.2 kilometers per hour. Acceleration of gravity. If we drop an object and it falls down to the earth, then the object will exhibit an acceleration, i.e. it is a constant acceleration, i.e. the velocity is increasing in a constant rate. Now, and near Earth surfaces, the acceleration of gravity is the same for all objects, and we call it the acceleration of gravity G. Now, the acceleration of gravity applies strictly only in free fall, and in free fall we mean that motion under the influence of gravity alone, neglecting the air resistance, and equal approximately to 9.8 meters per square seconds. Now, that means that if we have constant acceleration, then we can apply the equations of motions, but instead of writing A, we have to write G, and since G is directed toward the Earth's surface or downward, then the acceleration in this case will be minus G, and we are going to write, instead of X, we will write Y to designate a vertical direction, because in the motion near this in the free fall motion we have vertical motion. We have vertical motion, so motion in the y-axis. So the equations of motion will be, the first equation, for example, will be V2 or V equals V0 minus GT. The second equation will be Y minus Y0 equals V0 T minus 1/2 GT squared, and the third equation will be V squared equals V0 squared minus 2G Y minus Y0. And we apply these equations by the same manner that we apply the equations of motion with constant acceleration discussed in the previous sections. Now let's see an example about the acceleration of gravity. A diver drops from a 10-meter height cliff. So we have a cliff here and a diver, and the cliff is 10 meters high, of course, from the water. At what speed does he enter the water? So we are asked about the speed at which the diver enters the water, and how long is he in the air. So B, how long is the diver in the air? Let's see what are the conditions here. We have a diver at height 10 meters, so let's suppose that this is Y0, which is 0, and V0 of course is 0. This is the speed at which the diver drops, and we have here Y equals minus 10 meters, because the displacement here is directed downward, and the velocity or the speed is v, and we need to find v. And in order to find v, so part A, we need to find v. In order to find v, we have v0, and we have the acceleration, of course, acceleration, which is minus g. And in this case, in order to find v, we can just use this relation, v squared equals v0 squared plus 2 or minus 2gy minus y0. So v squared equals 0, v0 is 0, minus 2 times 9.8 times y, which is minus 10, minus y0, which is 0, or v squared equals 196, and so v equals 14 meters per second. And of course, because the velocity at the surface of the water is directed downward, so we have to write the minus sign here. This is the velocity of the diver at the surface of the Earth's surface of water. B, we need to find the time. We need to find the time the diver is in air. In order to find the time, we simply use the first equation of the equations of motion. V equals v0 minus gt, or minus 14 equals 0 minus 9.8 t, or simply t equals 1.4 seconds. Another example on the acceleration of gravity. You toss a ball straight up at 7.3 meters per second. This is the initial velocity of the ball. It leaves your hand at 1.5 meters. It leaves your hand at 1.5 meters above the floor. And find when it hits the floor. Asked about t, and the maximum height it reaches, and its speed when it passes your hand on the way down. So we have here a ball at 1.5 meters height, and the ball is tossed upward, so v0 is 7.3 meters per second. The ball then reaches maximum and go back to the Earth's surface. So if we suppose that this is y0 equals 0, so y here is equal to minus 1.5 meters, because it is directed downward. And in order to find t, we can use this equation. Y minus y0 equals v0 t minus 1/2 g t squared. v0 t minus 1/2 g t squared. Y minus y0 is minus 1.5 minus 0 equals v0 is 7.3 t minus 1/2 times 9.8 t squared. So this is a quadratic equation and can be solved to get two values for t. The first value of t is minus 0.18 seconds, and the second value is 1.7 seconds. So we neglect the minus time here. The minus time here is neglected because time cannot be negative. So the value of t is 1.7 seconds. This is the value of t. Okay. Now we need to find the speed when it passes your hand on the way down. So we need to find v here. And in order to find v, we can simply use this equation, v squared equals v0 squared minus 2g y minus y0, and the difference in y between the point the ball was tossed and the point when it passes hand again is 0. So this value is 0. So here v squared equals v0 squared. Solving this equation, we get v equals minus v0. The minus sign here is because the velocity of the ball is directed downward when it passes hand again. So v is equals to minus 7.3 meters per second. C, we need to find the maximum height. So we solved for the velocity before the maximum height. Okay, no problem, we can find the maximum height. So in this case we need to find the maximum height, and in order to find the maximum height we can simply use the fact that the velocity of the ball is 0 when it is at its maximum height. So here v is equal to 0, and simply we can use this equation, v squared equals v0 squared minus 2g y minus y0. 0 is equal to v0 minus 2g. 0 is equal to v0 squared, which is in this case 7.3 squared minus 2 times 9.8 times y minus y0 is y minus 1.5. In this case we can find the position of the height of the ball from the surface of the earth. The height of the ball from the surface of the earth, because we mean by y here all the height from the maximum point to the surface of the earth. Solving for y in this equation, we get simply 4.2 meters. And this is the maximum height the ball reaches. You are allowed 40 minutes to drive 25 miles to the airport, but you are caught in heavy traffic and average only 20 miles per hour for the first 15 minutes. What must your average speed be on the rest of the trip if you are to make your flight? So here we have a one-dimensional problem involving two travel segments. We are asked to calculate the average velocity for the second segment of the trip. So we have here two time intervals, t1 and t2, and actually t1 plus t2 is equal to 40 minutes. What we are given also is the t1, the first time interval, is 15 minutes. So here the total time 40 minutes. Here is the time for the first interval, and
we have also total distance of 25, so x equals 25 miles. This is the total distance that you have to drive to reach the airport. So, and we have two distance segments, x1 and x2, corresponds to t1 and t2, x1 and x2, and x1 plus x2 is simply 25 miles. So we have here t1 plus t2, which is t 40 minutes, which is 2/3 hours, and the first time interval is 15 minutes, which is 1/4 hour. Here we need to find the average speed that we should go with in order to make the flight. Actually, we have to find x2. If we know x2 and t2, if we know x2 and t2, we can simply find v to average, which is simply x2 over t2. T2 could be found by subtracting t minus t1, and t is 2/3 hours and t1 is 1/4 hours. This is t, the total time, and this is t1, this is t, and this is t1. So t minus t1 is 2/3 minus 1/4, and this is equal to 8 over 12 minus 3 over 12, which is 5 over 12 hours. This is T2. And x1 is simply x2 is simply x minus x1. But we don't know here. We know here neither x1 nor x2. So we have to find x1. How can we find x1? Simply v1 is x1 over t1. That implies that x1 equals v1 t1. v1 is 20 miles per hour times t1 is 1/4 seconds, 1/4 hours. So x1 is equal to 5 miles. So simply x2 is x minus x1, which is 25 minus 5, which is 20 miles. This is x2. Now we can calculate v2. v2 is equal to x2 over t2, 20 miles, divided by t2, 5.12 hours, and 20 miles over 5 over 12 is 48 miles per hour. In order to make my trip, I have to average 48 miles per hour in the second part of the motion. We can simply find the average velocity of the overall trip. And the average velocity of the overall trip is the total distance divided by the total time. The total distance is 25 miles over 2/3 hours. 25 miles over 2/3 hours is 37 miles per hour. You drive 4,600 kilometers from coast to coast of the United States at 65 miles per hour, i.e. 105 kilometers per hour, stopping an average of 30 minutes for rest after every 2 hours of driving. A. What is your average velocity for the entire trip? And B. How long does the trip take? This is a one-dimensional problem involving a number of time intervals, divided time intervals, and the key concept here is the average velocity. Now we can find the average velocity for each time segment, for each time trip, for each driving time using the relation V equals delta x over delta t. And to find and we know that the average velocity for each driving time is 105 kilometers per hour. From this relation we can find delta x, and delta x is equal to V average times delta t. V average is 105 and delta t is 2, and this is equal to 210 kilometers per hour. Now the actual time interval here is not only 2, but it is 2.5 because for each 2 hours driving time we have 0.5 hours stopping time. So delta t in this case is 2 plus 0.5, and this is equal to 2.5 hours. And so the average velocity, the overall average velocity for the driving time and the stopping time is delta x again over delta t. In this case delta x is 210 and delta t is 2.5, and this is equal to 84 kilometers per hour. And actually this is the average velocity for the overall trip, because the average velocity for each driving time is constant and the stopping time is always 0.5 hours for each 2 hours of driving. So this is the average velocity for the overall trip. This is A. And B, we need to find the total time required for this trip. Total time is simply delta t is delta x over V average, and delta x is 4,600 kilometers, which is the length of the trip, over the average time is 84 kilometers per hour, and this is equal to 54.8 hours. An object position is given by x equals bt plus ct squared. So this is ct squared, where b equals 1.5 meters per second and c equals 0.640 meters per square seconds, and t is time in seconds. To study the limiting process leading to the instantaneous velocity, calculate the object's average velocity over time intervals from 1 to 3 seconds, from 1.5 to 2.5 seconds, and from 1.95 to 2.05 seconds. And D, find the instantaneous velocity as a function of time by differentiating and compare its value at 2 seconds with your average velocity. So we need to find the average velocity over the given time intervals. Let's find, so we need to use this relation, V average equals x2 minus x1 over t2 minus t1. So we need to find x for each time given here. A, x1 is, we substitute t equals 1 in this relation. x1 equals b, which is 1.5 times t, which is 1.00, plus c, which is 0.640 times t squared, which is 1.00 squared. Calculating this, we get x1 is 2.140 meters. And the same for x2. The same for x2. If we substitute t equals 3 in this equation, we get x2 equal to 21.78 meters. And calculating the average velocity, V average is equal to 21.78 minus 2.14 divided by 3 minus 1, and this is equal to 9.82 meters per second. This is V1 or VA. The velocity corresponds to part A. The same for B. For B, we find x1 as before by substituting 1.5 instead of t in this relation to get x1 equals 4.410 meters and x2 to get 13.75 meters, and VB average is x2 minus x1 over t2 minus t1, the same, to get 9.34 meters per second. And the same for part C, we can find that VC average is equal to 9.18 meters per second. So we have here three velocities: VA 9.82 and VB 9.34 and VC 9.18 meters per second. Second, D, we need to find here the instantaneous velocity as a function of time by differentiating. So we have to differentiate the relation, this relation, x equals bt plus ct cubed, x equals bt plus ct cubed. If we differentiate it, we get v instantaneous is equal to b plus 3ct squared. And in order to find v at t equals 2, we just substitute instead of t 2 seconds to get b, which is 1.50 plus 3c, which is 0.640 as given by the problem, 0.640 times 2 seconds squared. Times 2 squares. Calculating this, we get 9.18 seconds. What can we note here is the value of the instantaneous velocity at t equals, or before that, we have to notice that the average time for each interval of time is the same, which is 2 seconds. So from 1 to 3, the first interval of time, from 1 to 3, the average time is 2. So we are calculating the average velocity around 2 seconds. And here the same, 1.5 to 2.5 seconds. And here is the same, 1.95 to 2.05 seconds. We can notice also that the time interval is decreasing as we go from A to C. So in A, the time interval is 2 seconds. In B, the time interval is 1 second. And in C, the time interval in 0.1 seconds. And we can notice also that the instantaneous velocity, V, the instantaneous velocity is 9.18 seconds. And the instantaneous velocity is equal to the velocity of the time interval at C. So, as the time interval is getting shorter, we are going closer to the instantaneous velocity. The first time interval 1 to 3 is farther from the instantaneous velocity because the time interval is 2 seconds, but it is closer, the instantaneous velocity is closer to the average velocity of the time intervals of B, and it is much closer to the time interval of C because the lowest time interval of the 3 intervals. An object's position as a function of time t is given by x equals bt to the fourth, where b is constant. B is constant. Find an expression for the instantaneous velocity. So we need to find v and show that the average velocity over the interval time from t equals 0 to any time t is 1/4 of the instantaneous velocity at t. So we need to find v instantaneous first of all, and we need to find average velocity from 0 to t, and to prove that the average velocity from 0 to t is equal to 1/4 the instantaneous velocity. Now, to find the instantaneous velocity as a function of t, we need simply to derive x with respect to t. So we need to derive this relation. This is simply equal to to 4bt cubed. This is the instantaneous velocity at time t. But to find the average velocity, we have to use the relation x of t minus x of 0 divided by t minus 0. Now, x of t is bt to the fourth, and x of 0 is b0 to the fourth divided by t. This is equal to bt to the fourth divided by t, and this is equal to bt cubed. And actually, this is 1/4 v instantaneous. So v average is equal to 1/4 v instantaneous. Now, in a drag race, the position of a car as a function of time is given by x equals bt squared. So we have a drag race, and the car is moving, and the position of the car is given by this relation as a function of time. The value of b is a constant, and its value is 2.000 meters per square second. In attempt to determine the car's velocity midway down a 400 meters track, so we have a 400 meters track. Two observers stand at the 180 meters and 220 meters. 180 meters. The first observer stands here, and the second observer stands here at 220 meters. Now, the observers are noting when the car passes. So we need to find the average velocity as computed by the two observers in the 400 meters track. We need to find the average. First of all, we have to find the instantaneous velocity from this relation. So V is simply equals to dx by dt, which is 2bt. Now, if we substitute instead of t from this relation, from the relation of the position, we can simply write V equals 2b. Instead of t, we substitute square root of x over t, because from this relation t is equal to square root of x over b, x over b. And so we must not forget plus minus sign. So this is equal to plus minus 2 square root of xb. Square root of xb. Now, in order to find the average velocity, we need to find the velocity, the instantaneous velocity when the car passes from near each observer, and the time the car needed to arrive the observers. So we need to find T1, the time needed for the car to arrive, to reach the first observer, and T2, the time needed for the car to arrive the second observer. The time, we can simply find the time from the relation t is equal to square root of x over b from this relation. So T1 is equal to plus minus square root over x over b, and this is equal to square root over x1, which is 180 meters, over b, which is 2.000 meters per square second. Evaluate this, we obtain 9.48 seconds. And the same for T2. For T2 is equal to square root over x over b. This is equal to square root of 220 meters, or 2.000 meter per square second. Evaluating this, we obtain 10.49 seconds. So we have T1 and we have T2, and to find the average velocity, x2 minus x of 1 over t of 2 minus t of 1, or T2 minus T1. So this is 220 meters minus 180 meters over 10.49 minus 9.48, and this is equal to 40.00 meters per second. Now in part B, we need to find the percentage of the instantaneous velocity with respect to the average velocity. Sorry, this value is 39.95. The percentage needed is, so V, we need to find V instantaneous. V instantaneous in this case is equal to plus minus 2 square root of xb. This is obtained by substituting from t from this relation. If we substitute square root of x over b, we obtain v equal plus minus 2 square root of xp, and plus minus 2 square root of xp is equal to square root of 200 meters multiplied by 2,000 meters per square second. And evaluating this, we obtain 40,000 meters per second. Now the percentage needed is simply 40.00 minus 39.95 divided by 40.00 times 100%, and this is equal to 0.13%. A particle leaves its initial position x0 at time t equals 0, moving in the positive x direction with speed v0, but undergoing acceleration of magnitude a in the negative x direction. So a particle at x0 moving in the positive x direction, but with acceleration in the negative x direction, he arrives some point x and then returned back to x0. We need to find an expression for the time when it returns to x0. So in order to find the time, we can use this relation: x equals x0 plus v0t plus 1/2 a t squared. But in this case, a is equal to minus a, and x is equal to x0 because it returned back to its initial position. So if we substitute x0 equals x0 plus v0t plus 1/2 minus a t squared. So v0t is equal to 1/2 a t squared. Cancelling t with the square from here, we obtain t equals to 2v0 over a. This is part A of the problem. And in part B, we need to find its speed when it passes this point. In order to find the speed, we have t. So simply v is equal to v0 plus a t. And this is equal to v0 plus a, and in this case a is minus a, and t is 2v0 over a. And this is equal to 2 minus, so v0 minus 2v0, and this is equal to 2 minus v0. And if we need to find the speed, which is the absolute value of the velocity, we obtain square root of absolute value of minus v0, and this is equal to v0. A jetliner touches down at 220 kilometers per hour, so v0 is equal to 220 kilometers per hour, and comes to a halt 28 seconds later. So v is equal to 0 and t is equals to 29 seconds. What's the shortest runway on which this aircraft can land? So it's asking about x minus x0. Simply x minus x0 is equal to 1/2 v0 plus v times t. Substituting 1/2 v0, in this case we need to find the units of velocity from kilometers per hour to meters per second, or we can convert t from seconds to hours. So let's convert T from seconds to hour, and the velocity, and let the velocity unit stays in kilometers per hour. So 220 kilometers per hour, and V is 0 as we mentioned here, times T in this case is 29 seconds over 3,600 seconds per hour. Evaluating this, we obtain 0.98 kilometer. So the jetliner needs 890 meters to come at halt 29 seconds when it touches down at 220 kilometers per hour. A motorist suddenly noticed a stalled car and slams on the brake, negatively accelerating at 6.3 meters per square second. So the motorist was going at speed V and acceleration A minus 6.3 meters per seconds per square seconds. Unfortunately, this is not enough, and a collision ensues. From the damage sustained, police estimate that the car was going 18 kilometers per hour. So V in this case is 18 kilometers per hour. This is equal to 18 times 1,000 divided by 3,600, and this equals to 5.0 meters per second. So estimates that the car was going 18 kilometers per hour at the time of the collision. They also measure skid marks 34 meters long. So X minus X0 in this case is for 34 meters. A, how fast was the motorist going when the brakes were first applied? Simplest way to find V0, we have A and we have V and we have X. To find V0, we simply use this relation, V0 V squared equals V0 squared plus 2AX minus X0. And V, which is, and we need to find V0, so we substitute instead of V 5.0 squared equals V0 squared plus 2 times minus 6.3 times 34. And if we evaluate this, we obtain V0 is equal to 21 meters per second. And this is the speed that the motorist was going when the brakes were first applied. In part P, how far did it, no, in part P, how much time elapsed from the initial braking to the collision? We need to find T. And in order to find T, we use the first equation of motion, V equals V0 plus AT. V is 21, V0 is V, V0 is 21, plus A is minus 6.3 times T, which is wanted. So T equals 0 is 21 and V is 5. T equals 5 minus 21 over minus 6.3, and this is equal to 2.6 seconds. After 35 minutes of running at the 9 kilometers point in a 10-kilometer race, you find yourself 100 meters behind the leader and moving at the same speed. What should your acceleration be if you are to catch up by the finish line? Assume that the leader maintains constant speed. Assume that the leader maintains constant speed. So we have here a race. We have a 10 kilometers race. And you are here at 9 kilometers point, and behind, let you be A and the leader be B, and you are 100 meters behind the leader. So you still need 1 kilometers to finish the race, and you spend 35 minutes to arrive this point, the 9 kilometers point, and also the leader spends 35 minutes to be at 9.1 kilometers, because we have here 9 kilometers and 100 meters. We need to find the acceleration needed by you in order to be catched at the finish of the race. Now, in order to find this problem, we need to find the leader's velocity. And the leader's velocity can simply be found by using the definition of velocity, which is delta x over delta t. And in this case, delta x is 9 kilometers plus 0.1 kilometers, which is the 100 meters, times 1000 meters per kilometers, in order to convert units from kilometers to meters. This is divided by 35 minutes multiplied by 60 seconds per minute. Evaluating this, we obtain 4.33 meters per second. This is the velocity of the leader, and this is also the velocity of you, the person A. In order to find the time needed for the leader to pass the remaining 900 kilometers, these 900 kilometers, we simply divide 900 over the velocity, which is 4.33, 900 meters over 4.33 meters per second. This is equal to 207.7 seconds. These 207.7 seconds are needed by the leader and by you to arrive the ending point of the race simultaneously. Now we need to find your initial velocity, your velocity at the 9 kilometers point, and the velocity of u VA is equal to delta x over delta t, and delta x is 9,000 meters divided by 35 minutes times 60 seconds per minute, and this is equal to 4.29 seconds. Now we need to find the acceleration of person A, the acceleration of u, in order to be catched at the end of the race. Now what we have here is the initial velocity v0a, which is 4.29 seconds. We also have the time, which is 207.7 seconds, and we have x, in this case is 1 kilometers, which is 1000 meters. And we can use this relation, x, of course, x of a, xa is equal to v0 at plus 1/2 a t squared. X is 1000 and v is 4.29 times t 207.7 plus 1/2 a times t, which is 207.7 squared. Solving for a, we get a equals 0.0051 meters per square second. You're atop a building of height h, and a friend is poised to drop a ball from a window at h/2. Find an expression for the speed at which you should simultaneously throw a ball downward so the two hit the ground at the same time. So you have a building which is h height, and you are here. You're going to throw a ball with velocity v0, and actually it is minus v0 because the velocity is directed downward, and your friend stands here at h/2 height and is going to draw another ball, but in this case free fall. So v0 is 0 in the case of your friend, and we need to find the velocity that with which you should drop the ball in such that the two balls hit the ground simultaneously. We can use the equations of motion for the two heights here, the h height and the h/2 height. Simply we can say that we know that y is equal to y0 plus v0t plus 1/2 at squared, and in this case a is minus g, and y minus y0 is minus h, so minus h is equal to minus v0t minus 1/2 gt squared, or in other words h is equal to v0t plus 1/2 gt squared. This is for the first ball, for your ball, and for the second ball we can say minus h/2 is equal minus 1/2 gt squared, because v0 for the second ball is 0, and the time for the two balls should be the same in order to hit the ground simultaneously. And from equation 2 we can conclude that t is equal to square root of h/g. Now what we are going to do now is to substitute instead of t from this relation in this relation. So h, if we rewrite this relation, h is equal to v0 square root of h/g plus 1/2 g square root of h/g squared, or h is equal to v0 square root of h/g plus 1/2 g h/g. G is cancelled with g, and rearranging this relation we obtain h/2 is equal to v0 square root of h/g, or in other words v0 is equal to h/2 square root of g over h. This is equal to 1/2 square root of g h. So this should be your velocity in order for the two balls to hit the ground simultaneously. Two drivers jump from a 3-meter platform, one just upward at 1.8 meters per second, and the second steps off the platform as the first passes it on the way down. What are their speeds as they hit the water, and which hits the water first and by how much? So in this problem we have a platform here which is 3 meters height, and we have two drivers, driver A and driver B. Driver A jumps upward at speed v0. A equals 1.8 meters per second, and the driver B slips off the platform as driver A passes him. We need to find first of all the velocity at which the two drivers hit the ground. So we need to find VA and we need to find VB. In order to find VA, we can simply apply the equation of motion VA squared equals V0A squared plus 2AX minus X0. And if we take into consideration that at this point X0 equals 0 and at this point X equals minus 3.00 meters for both A and B, then VA squared is equal to 1.8 meters per second squared plus 2 times the acceleration of gravity is 9.82. We have to keep two significant figures as mentioned in the problem. So minus 9.82 is the acceleration of gravity times x, which is minus 3.00 minus x0, which is 0 in this case. And solving for VA, we can find VA to be minus 7.88 meters per second, where we take the minus sign for the velocity because the velocity is directed downward at the time A hits the water. And the same we can, this is part A, and the same we can find the velocity of B when it hits the ground. VB is equal to V0, VB squared is equal to V0B squared plus 2AX minus X0. V0P is 0 plus 2 times 9.82. 9.82 is the, as mentioned above, the velocity, the acceleration of gravity minus the minus sign times minus 3.00 minus 0, and solving for VB, we get VB equals minus 7.67 meters per second. As we can mention here, the velocity of, as we can notice here, the velocity of VA is greater than the velocity of B. That's because the velocity of B is greater than that of A when it passes it. When A passes B, it has a greater velocity, so it has a finally greater velocity when it touches when it hits the water. In part B, we need to find the time for who hits the ground first. Who hits the ground first? I.e., we need to find the time for VB from the time he slips the platform to the time he hits the water, and the time for driver A from the time he passes B to the time it hits water. Let's find first of all the time for driver B. In order to find the time for driver B, we use the equation of motion, the equation of constant acceleration. XA is equal to X0A plus V0AT plus 1/2 A T squared, and solve for TA, solve for T to find the time for T from the time he passes B to the time he hits the water. XA is minus 3.00 meters equals X0 is 0.00 plus V0A in this case is minus 1.8 meters per second time T plus 1/2 minus 9.82 multiplied by T squared, and we choose the velocity of A to be minus 1.8 meters because we need to find the time from we need to calculate for the time from passing A, from passing B, the time at which A passed B to the time it hits the ground. And when A passed B, he had a velocity minus 1.8 meters per second, which is the same velocity, the same jumping velocity for A, but in the minus sign because the velocity is directed downward in this case. And solving for A, solving this relation for TA, we find TA equals 0.0883 seconds. The same for B, xB is equal to x0b plus v0b t plus 1/2 at squared, and x0 is 0 and v0b is 0, so xb, which is in this case minus 3.00 meters, is equal to 1/2 times minus 9.82 meters per square seconds multiplied by t squared. Solving this relation to find t, we can find tb to equal 0.782 seconds. It's the time for B and this is the time for A. As we can see here, the time for B is greater than that of A. That's because the initial velocity of A is greater than that initial velocity of B. And to find the difference in time between A and B, delta T, we can simply subtract TA from TB. So TB minus TA, and this is equal to 0.782 minus 0.0883. This is equal 0.693 seconds. This is the time between the time at which the first driver hits the water and the time at which the second driver hits the water. A balloon is rising at 10 meters per second when its passenger throws a ball straight up at 12 meters per second relative to the balloon. How much later does the passenger catch the ball? So this is a one-dimensional constant acceleration problem. We have a balloon which is rising at 10 meters per second and a person which throws a ball upward with a velocity of 12 meters per second. So we have two objects here, the balloon or the person and the ball. The person catches the ball when they are at the same position. So if we can simply equal the position of the balloon with the position of the ball. So y balloon, let's take the coordinate system to be the y-axis because it's a one-dimensional problem. So y person equals to y balloon. Because the person is rising up at constant speed, we can use the relation v person t, and because we have an acceleration of gravity for the ball, we can write vbt minus 1/2 gt squared. And solving for t, we can find the time at which the person catches the balloon here. And the velocity of the balloon is simply 10 meters per second times t is equal to the velocity of the ball, the initial velocity of the ball v0t. The initial velocity of the ball is 12 meters per second times t minus 1/2 and g, which is 9.82 meters per square seconds time t. And solving for t, in this case we have two values, 0 and the second value is 2.4 seconds. Of course 0 is the time at which the person throws the ball. We don't need this time, but we need this time, 2.4 seconds, which is the time at which the person catches the ball. Landing on the moon, a spacecraft fires its rockets and comes to a complete stop just 12 meters above the lunar surface. It then drops freely to the surface. How long does it take to fall, and what's its impact speed? Now, this is a one-dimensional problem involving a spacecraft that is landing on the moon. this is a gravitational, this is a motion in the gravitational field of the moon, and we can use the first constant acceleration equations, but taking into consideration that we have to use the acceleration of gravity of the moon, not the acceleration of gravity on the Earth. And the acceleration of gravity of the moon, G moon, is equal to 1.62 meters per square seconds. Now, in order to find the falling time of the spacecraft, we can simply use the equation of motion, the equation of constant acceleration. X of t is equal to x0 plus v0 t plus 1/2 a t squared, and a in this case is minus g, so and x0 is 0 and v0 is 0 also, so x is equal to 1/2 a t squared, so minus 12 is equal to 1/2 1.62 minus 1.62 t, and evaluating t, here t is equal to 3.9 seconds. This is the first part of the problem. The second part of the problem, we need to find the velocity at which the spacecraft hits the lunar surface. Simply v is equal to v0 plus a t. This is equal to 0 plus minus 1.62 times t, which is 3.9, and this is equal to 6.2 meters per second. Now, what if the spacecraft is landing on the Earth? If the spacecraft is landing on the Earth, we have to use, instead of minus 1.62 meters per square second, here we have to use 9.82 meters per second. So v is equal, so on Earth v is equal to minus 9.82 times 3. No, and the time is not 3.9. In this case, the time is 2 times 12 over 9.8 squared. 2 times 12 divided by 2v over g. 2v over g squared, 9.82 squared, and this is the acceleration of the acceleration of gravity on the Earth. Evaluating this, we get approximately 15 meters per second. This is approximately 5 times the velocity in the case, or 3 times the velocity in the case of landing on the moon. You are an investigator for the National Transportation Safety Board, examining a subway accident in which a train going at 80 kilometers collided with a slower train traveling in the same direction at 25 kilometers per hour. Your job is to determine the relative speed of the collision to help establish new crash standards. The faster train's black box shows that it began negatively accelerating at 2.1 meters per square seconds when it was 50 meters from the slower train, while the slower train continued at constant speed. What do you report? Now, this is a one-dimensional problem in which we have two objects or two trains. A train is going with constant velocity, and a train is decelerating at a rate of minus 2.1 meters per square second. We need to find what was the velocity of the faster train when it collides with the slower one. And in order to find the velocity, we can use the equation of constant acceleration. Vf is equal to Vf square is equal to Vf0 square plus 2a x minus x0. Vf, we need to find it. Vf0 is simply 18 kilometers per hour square plus 2a, a is minus 2.1 meters per square seconds, times 50 times the conversion factor from meters per second to kilometers per hour and from meters to kilometers. So we have to multiply this by 3,600 seconds per hour divided by 1,000 meters per kilometer. Okay, this is squared. Evaluating this, we obtain 60.6 kilometers per hour. And relative velocity for the two trains, relative velocity of the faster train with respect to the slower train is 60.6 minus 25, which is 36 kilometers per hour. So the relative velocity of the two trains when they collide was 36 kilometers per hour. Now, in order not to have a collision, the velocity of the faster train had to be less than the velocity of the slower one at the time of collision, or at the time it touches the slower one. A particle's position as a function of time is given by x equals x0 sine omega t. So x equals x0 sine omega t, where x0 and omega are constants. X0, omega are constants. A, find expressions for the velocity and acceleration, and B, find what are the maximum values of velocity and acceleration. So we need to find first of all the velocity of this particle and the acceleration also. The velocity is given by the derivative of x with respect to time, so we have to derive this equation with respect to time. dx by dt, in this case dx by dt is omega x0 cosine omega t. The derivative of sine is cosine, and in order to find the acceleration we have to derive the velocity with respect to time, or to derive the velocity with respect to time, or the second derivative of the position with respect to time, the position function with respect to time. So we have to derive this function with respect to time to find the acceleration, and the derivative of this function is omega squared x0 minus sine omega t. The derivative of cosine is sine, and this is the acceleration function. In part B, we need to find the maximum values for V and A. The maximum value for the velocity, first of all, we all know that the maximum value of the cosine function is 1. So the maximum value of the velocity will be omega x0 times 1, which is simply omega x0. And the same for the acceleration, a maximum. From this function, we can conclude that the maximum value of the acceleration is omega squared x0. And actually, this is the function of the simple harmonic oscillator that we are going to talk about later. A police radar effective range is 1 kilometers, and your radar detector range is 1.9 kilometers. You are going 110 kilometers per hour in 70 kilometers per hour zone when the radar detector beeps. At what rate must you negatively accelerate to avoid speeding ticket? So the driver in this case has to arrive the range of police radar detector area at a velocity of 70 kilometers per hour. So the driver has 0.9 kilometers, x minus x0 in this case is 0.9 kilometers. He has only 0.9 kilometers to decrease his velocity from v0 equals 110 kilometers per hour to v 70 kilometers per hour. So in order to find the acceleration of the driver, in this case we can use this relation: v squared is equal to v0 squared plus 2ax minus x0. V squared is 70 kilometers per hour squared equals 110 kilometers per hour squared plus 2a times x minus x0, 0.9 minus 0 in this case. And solving for a, we get minus 1.11 kilometers, 1.11 kilometers per square hours. This is the acceleration that the driver should exhibit in order not to have a police ticket. An object starts moving in a straight line from position x0. So at t equals 0, x equals x0, and v equals v0 also, as mentioned in the problem. At time t equals 0, the velocity v0, its acceleration is given by a. The function of acceleration is a equals a0 plus bt, where a0, b are constants. Find expressions for the instantaneous velocity and b the position as a function of time. So we need to find the instantaneous velocity, and second b, we need to find the instantaneous position as a function of time. Note here that the acceleration is not constant, so the equations of constant acceleration are not applied here. And in order to find the instantaneous velocity, we have to integrate. In order to find the instantaneous velocity, we should integrate the acceleration with respect to time. So the integration of a0 plus bt dt. Evaluating this integration, we get a0t plus bt squared over 2 plus c1 constant. In order to find c1, we know that v equals v0 at t equals 0. So substituting 0 here, v0 equals 0 plus c1 implies that c1 is equal to v0. So the acceleration, so the velocity, the instantaneous velocity is equal to a0t plus bt squared over 2 plus v0. Now, for the instantaneous position, we just integrate the velocity with respect to time. V dt, this is equal to the integration of a0t plus bt squared over 2 plus v0 dt. Evaluating this integration, we get a0t squared over 2 plus bt cubed over 6 plus v0t plus a constant c2. in order to find this constant, we use the fact that x equals x0, x equals 0, x equals 0 as mentioned, no, x equals x0 at t equals t0 as mentioned in the problem. X equals x0 at t equals t0. We can conclude from here that z2 is equal to x0. So the position function as the position function here, the position as a function of time is x0, which I substituted instead of c2 here, plus v0t plus 1/2 a0t squared plus 1/6 bt cubed. This is the function of position. Oh, this is the position as a function of time.